We're here with Scott in the metrology lab, and we're going to do some interesting testing on fasteners, but to do that we're going to use a pretty interesting tool here, which is like a bench tester for torques and loads. So Scott, how does it work?
We have our drive motor that we can control RPM and speed with. It also communicates with the other tools to shut down at certain shutdown points. In line here with the drive, between the socket drive and the motor, is our transducer for the amount of input torque and angle rotation. So it's a kind of a dual instrument.
So on that half of it, basically it's just a big old torque wrench that's automated.
Correct.
Okay.
And we're getting, again, our torque and angle measurements from this device here. On our clamp load cell, we have dual transducers. One of them's picking up the clamp load that's being achieved as we're tightening down the fastener. On the rear end of this, it has a transducer that's capable of picking up torque once again, but we're going to call it thread torque. It's the amount of torque that's being transferred through the fastener into the back of the machine. So in a stud, it'd be what was being transferred down to whatever the stud is inserted in. On a bolt setup, it'd be the torque being transferred back to the nut.
So am I thinking about it correctly if I think about like that's sort of the amount of twist that we might be getting in the fastener, or how much it might be turning in the socket? So effectively there's a couple different ways we could look at this data. For a guy that's an engine builder and using a fastener and using a torque wrench, we can either measure, let's say I keep the torque constant and I do the same torque every time and apply different lubricants to the fastener and see how much that changes my clamp load.
Correct.
Or we could say we have a target for clamp load that we need to make all of our system work properly, so we're going to put the fastener in there with various types of lubricants, and we'll see the variation in torque that it takes to achieve that clamp force. Am I getting that right?
That's correct. Generally, we're trying to achieve a certain clamp force for the fastener. We know the load carrying capacity of the fastener based on its size and the alloy and its tensile strength. So if we want to try to get the most out of the fastener, say 75, 80% of up to the yield, that is a clamp force that we need to try to hit.
So that would be like your design spec when a customer comes to you and says, I got this project and I need this much clamp force. You guys have already designed that fastener to achieve that.
Again, every fastener, it has its own load carrying capability in a function of its size, its cross-sectional area, and the alloy, the tensile strength of the material. So we know what it's capable of doing. So if somebody wants to get the full capacity out of that bolt, whether it be 75% of the yield or 80% of the yield, we are trying to now define what is the torque to get there.
So you're basically making your spec card that you're going to give the customer. You're going to tell them, use this fastener, use this lube, and put this much torque in it, and then you'll achieve the clamp load that you want. You're trying to find that range for them? Is that how it works?
If we can control the fastener, which we make, any coatings are on the fastener, the nut, the thread, the lubricant, and how we lubricate things, the narrower window we can stay within to try to help get that target clamp load every time.
Well, cool. I'll tell you what, I'm going to get out of the way, and maybe you show us how it works. Let's put one in there and try it.
We'll do it.
Okay.
We have some studs here, 7/16 fine on one end, and the coarse end would be buried down in the product. Maybe it'd be a head or a block in this case. We say we don't necessarily remove the RP from the part, but one thing we do want to make sure is the washer is clean and had solvent cleaned and removed.
Okay. We
have a couple various lubricants here, the Torque Point Black. We try to utilize for 8740, 6304 black oxide type products.
Okay. If you're using more exotic materials, you'd change to something else?
So far, testing would suggest so.
Okay.
We're trying to get somebody to say, every time you torque this down using this method to this foot-pound measure, that we always hit that number we're trying to get to, and that'd be the clamp load.
Obviously, we need the right lubricant. How important is it to get the amount or area of lubrication? How much does that affect your results?
We put it on fairly liberally. I don't know that it would affect it.
Okay.
As long as the surfaces are coated with lubricant, I try to get it in all the thread flanks, You know, the hardest place to get the lube, that's what's bearing on the other component.
So it's a matter of I can maybe get too little, but you probably can't get too much?
I don't know that you can get too much. It just squeezes out and makes a mess.
Okay, gotcha. All right, well, so we're gonna try a few different ones then. We're gonna try some just straight motor oil and maybe some of this P1, 0.1 torque point. And then tell me about this peanut butter. I've heard guys in the industry talk about peanut butter, which is obviously some name that was given to this, whatever this chemical actually is, but tell us a little bit about that and why we want to look at it in this test.
Our experience with peanut butter is it provides a lower friction constant. A lower friction constant means you're going to hit your target clamp load at a lower torque.
Okay, that makes sense. So it's just reducing the friction, which means for a given amount of torque wrench action, I'm probably going to have lower clamping force, or if I have a target clamp force, I can get there at a lower torque value.
Correct.
And is that necessarily a benefit in all applications? In other words, if that's the case, why wouldn't I use that in everything from my lawnmower to a Boeing jet? I mean, I think this is really common in the diesel industry.
We find that the peanut butter performs best at higher flank pressures. What I mean by that is the contact stress on the flanks. So that's relative to, again, mainly the tensile strength of the material. Something like a grade 5 fastener where your flank to flank pressure would not be extreme, the nut to the fastener. But just, you know, if it was extreme, you're putting too much load on that bolt. You tend to have a lot of variation in the torque that's required to get there.
Okay.
And it seems to shine better when you get into higher flank pressures, such as higher strength fasteners where your torque's going to tend to climb.
So that would to me at least make sense why you see a lot of those in like the diesel industry where they have heavy big engines and lots of clamping force required, and so their flank pressure is higher because their torque values are higher.
And also some of our higher strength alloys.
Okay, your CA625s and your MP35, that kind of stuff.
Yeah, and H11.
All right, well let's shoot. Let's slather one up and see what happens. That's my favorite part.
All right.
I don't have my lab coat on or anything, but you know, I'll get through it.
Well, this is our tooling that's going to mimic whatever the stud's dropped into. It goes into the back of the machine. It's keyed in so it can't rotate.
Okay. So that's effectively like our block or our head or something.
Yeah, it's just holding it.
Is that tooling that's made here? You guys make that?
Yeah.
Okay.
You know, we run them in and just bottom them out.
Okay.
Just put a little, we put them in just a little snugness here. We don't necessarily torque them to anything or anything like that. We're just not wanting it to spin.
Okay.
When we're torquing down, we want everything to be constant. That's this rotation and this frictional component without something else popping or periodically snapping on you.
Yeah, we don't want more variables in there. So that side then does not necessarily need any lubrication.
I put a little oil in it just to keep our tool healthy.
Okay.
We suggest putting the lubricant on the male threads, the female threads of the nut, and the face of the nut, and nothing on the washer.
Okay, and why not on the washer?
Well, we want to control where the friction component is on the underhead.
Okay.
So we have two types of friction. You got the thread friction, and on a bolt it'd be the underhead of the bolt, or in the stud it's going to be the underhead of the nut.
Okay.
So those are your two components. And we want to control the friction of the underhead and have the lubricant active between the washer and the nut, not the nut and the substrate or member that the nut is on.
So the washer is going to have, like, say if it's in my cylinder head, the washer is going to have friction so it doesn't spin.
Right.
But my nut on the face of the washer is going to reduce that friction with the...
You know, and aluminums or something else, if you start to have a lot, you know, under a high compressive load and you're doing a lot of spinning of the nut, you'll scar up your surfaces.
Okay.
As long as that's there just to spread the load like its job without it turning, again, I think it'd be less wear and tear.
We don't want that thing
on softer
spinning
joints.
And, yeah, tearing up our thing. Okay, cool.
So again, we're controlling the friction on the underhead between our nut surface, machined to a certain RA, and the same as our washer, both black oxide. And another reason we wouldn't want this spinning on their member is we don't know what their member is. Maybe it's smooth, maybe it's slick, maybe it's not. Well, if it sometimes is moving and sometimes isn't moving, that's another factor can throw air into all this whole equation.
So that's interesting. I hadn't actually considered that the surface roughness on the face here obviously affects the amount of friction you would get. That's a key point that I hadn't thought about before.
We're just trying to eliminate the number of variables, and the more we can tighten up these variables or eliminate them gets us closer to achieving our target.
It's easier to predict the result that way. So we'll get our little paintbrush here. By the way, when you order these P1 fasteners, they supply the fasteners with lubrication and the little brush to paint them with. So nice little perk that you get.
Yeah, you use more of this stuff than what you'd think by the time you get all the way around it. So we have the fastener bottomed out into our tool. We have some stack up members here, spacers to simulate, the members being fastened together, just getting us offset to where a nut will be on the appropriate part of the fastener. So again, we're just stacking up thickness.
Taking up the space.
So again, we have our clean washer, not lubricated, a nut lubricated on thread and bearing flange.
So is that a direct, like, real-time readout?
Right here.
Oh, okay, yep.
We'll have the machine's going to go up to, we have it set to go to 20 foot-pounds.
Okay.
Stall, kind of like somebody who might be setting fasteners in some type of sequence.
Okay.
And at the 20 foot-pound mark, the machine will zero out the angle, so we have a zero. At some point, we have to zero something. We could say, well, we're going to zero it at finger tight. Well, what's finger tight?
Yeah.
Well, can you tell me how tight finger tight is? No, I can't. One thing I can tell you is if we zero at 20.
Okay.
Now, it saves the data before then. We just have a 0 point.
Okay.
It'll remember all the data that happens prior to that.
20 just gives you a place to start from the same spot every time.
Right. Now, we're not zeroing out any of the clamp force. Like right now, just barely finger tight is showing 5 pounds.
Okay.
But that's a true 5 pounds, so we'll leave that on. That all looks fine. Get this thing indexed on here. Shield here, just in case of a over-torquing event.
We're now firmly established in the region of hold my beer.
So we're ready to go here.
Okay, let's watch this thing go. I'm gonna stand back. So we see it came up to 20 and then it basically
It's just stalling over time.
stopped, yep. So we see the load going up completely linearly and then it just starts to...
I have this, yeah. While it may not be obvious on this particular graph, we get this thing records all the data at a predetermined data rate. We get the data and we can graph it and look at this behavior, and in this case is angle and clamp load, to look at this behavior. And again, we're looking for when this line becomes no longer proportional.
So where it bends there at the top is like, okay, now we're stopping. That's the beginning of the yield section, essentially.
Yeah, in this exercise, we can think of angle or the degrees of rotation directly related to length.
Okay.
One whole revolution is one pitch.
Mm-hmm.
One pitch has a length. Something had to give. The bolt stretched or the members shrunk.
Okay.
So in this case, for identifying the onset of yielding, we can use the angle.
Yeah, so it basically, at the end there, it traveled farther for a given unit of angle than it had previously.
Correct.
Okay, pretty cool.
And you could almost see where it's nearly beginning to flatline.
Uh-huh. And that was just over 20,000 pounds of actual clamping load.
Mm-hmm.
So now when you were to send this out to a customer, that specific load is higher than what you're hoping they were planning on using, I guess.
Sure. Well, in this case, we've clearly yielded the bolt. That is, we've permanently stretched it.
Okay.
We take the load off, and now the bolt is longer than it used to be.
Than when we started. Okay.
So In this particular case, I went ahead and just ran it up past yield to demonstrate this.
Okay.
Now you can still achieve and do your torque numbers down in here, but for this particular fastener, we wouldn't want to retest it again. It's no longer the same fastener.
Yep. But if you were going to take that same fastener family and then send it to your customer, would you go in here and say, my recommended torque is say between here and here somewhere, so maybe between 60 and 90, and that's what you would tell the customer to use?
Sure.
Okay.
Again, we'll better define this using a different software package.
Okay.
Where the slope is easier to identify.
Got it. Okay. So now we want to do that. That was with your recommended lube. What we're trying to find out is what if the customer doesn't use your lube? So we're going to do that and compare those? Is that what the plan is?
Sure.
Okay.
Well, one is we know that we're going to get a different friction behavior. It's a different substance. Some substances provide a slicker substrate than others.
Okay. Very interesting. It's a pretty cool toy. I think I probably need to get one of these. All right, that was pretty fun. So now what we're going to do is we got some of the identical fasteners here, and we're just going to do the same test over again, but instead of using the P1 torque point lube, we're going to put on some peanut butter, this industry kind of secret, and then we'll do it again and just use regular motor oil, and we're going to find out if we get a different clamp load based on that. Mm-hmm. Okay, very cool. Let's go ahead and get after it.
Well, these brushes actually work pretty good. Mm-hmm. They look pretty.
It's all about application. They're terrible for toothbrushes. Really good for this job. The right tool for the job. All right, so now we got the peanut butter in there, and we're going to run the same test over and see if there's any difference between that and the P1. All right, so we saw a little bit of difference in the friction kind of characteristics of the peanut butter versus the 0.1 lubrication, but probably not a huge difference there that we're going to see.
No, it wasn't on that run.
Okay.
But there was some difference.
Yeah, and we'll see some of that when we plot it out, but the last test we want to do is we're going to now go back to what happens if I just run straight old, engine motor oil and see if we can find a difference there.
You bet.
Okay. All right, well, as you're prepping it there, I'll take a look over here. We got a nice shiny new quarter, some fancy Valvoline 1040, traditional mineral-based oil, and I don't know that it would make any difference if it was mineral-based or synthetic-based. Point is, it's not a specific lubricant made for fasteners, and I'm just curious whether or not it makes any difference, so there's only one way to find out.
One more lubricant. Again, we're getting data. About 125 hertz out of each one of these channels.
Okay, it's pretty high speed.
Graph relative to relative, clamp load, input torque, thread torque.
Now we take all this data and put it in your other software. And
again, mainly interested in getting to the clamp load we want. First, we're going to define that by looking at the angle and where it comes off proportionality.
Okay.
We're going to come off of there 20% to the 80% of the onset yield. Then that's how we establish the clamp load we're trying to achieve.
Okay.
Then we're going to look at the relationship of clamp load and the input torque.
Okay.
And that's going to tell us what kind of torques are we looking to recommend for this product, depending on what lubricant it was.
Very cool. Can't wait to see that. All right, Scott, so we did a bunch of those tests yesterday and collected the data. Now your machine collects a lot of data, like 125 samples every second. So what you ended up doing then is took all that and plotted it in spreadsheets for us so we could visualize the data, right?
Correct.
We got a couple different charts to help explain what the end goal is. For most people, it's how much torque am I supposed to use? And of course the answer is, well, that depends. Walk us through real quick. This is both data we collected and the historical data that you have knowing about that fastener. So
Right.
walk us through this side of it, how you go through that.
That stud that we ran yesterday was the 7/16 fine on one end and a coarse on the other end. I don't know about the body diameter. It was a recent production part, so I had run several tests on it prior. So I have some historical runs on it. We did a couple, 2 or 3 runs yesterday demonstrating the effect or the impact of a changing lubricant. lubricants and how that would change a torque that we would recommend to achieve the clamp load you're wanting. It's a function of the properties of the fastener itself. It'd be 75 to 80% of the yield is what generally people are shooting for. Yield is a stress.
Yeah, that's a good point. Let's make sure that everybody knows what you mean when you say yield. Talk us through that.
You know, the steels, they elongate relative to the force you put on them. Linear or elastically up to a certain point. Their elasticity turns to plastic deformation.
So if I start pulling my ink pen apart, it will, basically stretch and get longer.
Or, if you bend it and you let go of it, it comes back.
Yep.
If you bend it, it doesn't come back, and it's plastically deformed.
So it's sort of like I think of Laffy Taffy, right? As I pull it, it gets skinny in the middle and I let go, and now it doesn't want to go back anymore.
Correct.
It's no longer my slinky.
Steel fasteners, you have to think of them as an extremely stiff spring that's able to be moved, elongated, bent, and also come back to its original shape and geometry.
And it's that property of wanting to return back to its original shape that's giving us our clamp force that we're trying to get.
Correct. Think of it as a spring. Mm-hmm. If the spring's overloaded and it doesn't return to its shape, it's been yielded.
It's not doing its job. Okay.
First, we're going to try to identify what forces, what clamp loads are required to actually start to yield this product.
Okay.
What I'm looking at here is the very onset of yielding, when it very first starts to function nonlinear.
Okay.
We have a graph here showing the relationship of the clamp load relative to the angle of rotation, in this case the nut. As the nut angle continues to increase, we know that the bolt is stretching, as well as the members in between which are fastening or compressing. So when does this system begin to operate nonlinear? This is a whole series of runs on that product that we had run prior to you all being here. This particular run here, it just stopped prior. I probably was not wanting to yield this product. Mm-hmm. I just wanted to get sufficiently up to have some information.
Okay.
Yesterday's runs were more like these, where we're trying to actually yield the product. Again, this relationship here, we're just going to look at one of the studs we'd run with the torque point lubricant. For the most part, you'll see that it's a linear relationship. The angle is advancing at the same rate as the clamp force or tensile load on the product is increasing.
So our slope is linear. Our rise over run here is staying very constant in the middle.
In here, we begin to see this line begin to drift off to the right. The angle is increasing faster than what the clamp load is now.
Okay. So that's because our part is starting to get yielded.
It's starting to go plastic to where it won't recover.
So it's no longer elastic, it's now plastic.
Correct. I try to draw straight lines here that follow the slope of this product. So we have a straight line. We're looking at this load versus angle relationship. When does the behavior of stud 4 go nonlinear? It's going to be the red line I have laid here as an average of the data set. We're looking at just one particular run here, but you can see that it's following the straight line and begins to walk off of the straight line and run to the right.
Okay.
That's an indication that we have gone nonlinear and we're getting to yield the product.
So that's the first onset of when we're starting to yield.
Correct.
So that's sort of your max. You don't want to exceed that number.
So we will have found the force for each one of these runs, the load that corresponds to when it begins to drift to the right. The average of the 4, we had 6 runs, but only 4 went to yield. We have onset yielding recorded, and the average being at 17,350. We're wanting to achieve 80% of that to keep you below yielding.
Okay.
Some safety factor.
So that gives you a 20% safety factor if you do the 13,880.
Correct. So we look at these values, the average of the data set of 17,350 and the 13,880. These runs are beginning to yield at the red horizontal line. We say, okay, well, that's the onset of yielding. We're looking for 80% of that load. 80% of that load brings us down to 13,880. 880. That's the green line scribed across. We've established the clamp load that's 80% of the yield.
Okay.
Now it's time to say, well, what torque did it take to achieve that?
So you get that question from a lot of guys. You tell him he needs the 13880, and of course he goes, okay, well, so what's my torque value? And you say, well, that depends.
And it does. We have to keep one thing common and tightly controlled, and that would be the friction factor, you know, between the thread flanks and under the head. These are, again, runs with our product, our nuts, and the torque point lubricant.
Okay.
And we did some runs yesterday, one oil and one with peanut butter.
So this will display then the effect that a guy would have if he decided not to use your fastener lubricant.
Correct. And the variations that you can see when you change lubricants.
Sure, yeah.
And the target on clamping something together and tightening a fastener is to generate the load that you want.
We're trying to hold those two parts together, so my fastener's got to be clamping them
We want
together.
to keep them tight. We don't want to be leaking air, leaking water, chafing, rubbing, loose joints lead to fatigue. Keep everything intact tightly so the load's in service. We're going to go over to another chart, and it's just going to show now we still have the clamp force or the tensile load on the bolt, and we're going to look at it as we tighten down these products, but now we're going to look at it as a function of the input torque.
So already we see a pretty huge variation. We have a bunch of them in the middle together, and then we have two big outliers.
This is the average in the data set using the torque point. They're relatively tight. We like to see that. You know, we want to be able to tighten down a whole series of fasteners and get the same result. Again, repeatability, bolt to bolt, bolt after bolt, bolt run 1, 2, 3. We're trying to get to that clamp load with confidence.
So those are what we could expect if we use the torque point's recommended lubrication. Let's talk about the outliers.
Keep in mind we have our green line. That's our target clamp load what we defined on the other chart. It's equivalent to 80% of the onset of yield.
Okay.
That's a fixed number for that product while under torque and tension.
Okay. So how much torque did it take us to meet the clamp load requirement using the torque point lube?
The torque point lube, one end of the range would be here, the high range there. We can do tabular averages like I've done up here, but for this application, we can just, let's put the line kind of near the middle of the data set.
Okay.
We're trying to get to the 13880, and we see that a torque of about 86 foot-pounds
will get us there.
will get you there.
Okay. So if we need 86 foot-pounds consistently with our torque point lubricant, let's look at how much torque we need if we use oil. Now the deal is oil is going to have less lubrication. It's not quite as slick as the torque point, so it's going to have more friction. Is that right?
Correct.
So if I have more friction, then I have to torque the fastener more to overcome that friction and get the clamp load that I want.
Correct.
Okay, so how much torque would it take me if I just used regular motor oil?
We did just one run yesterday. The data put on with our prior data set, we were tightening up, tightening up, tightening up. So we got to our target of the 13880 at a torque of about 119
Wow.
foot-pounds.
That's a big difference from 86 to 119.
Friction is huge.
So you were telling me when we were discussing earlier, a huge percentage of the torque that you're putting in is just consumed by the friction.
It is.
And now we can see that really graphically.
You have to think about, well, we're trying to convert torque energy into, stretching this product out, which takes energy, and converting one to the other. And there's a lot of friction that has to be overcome. Of your input energy, when you're putting input torque in, approximately 90% of that is wasted in friction.
Wow.
That would be a combination of the underhead friction as well as the thread-to-thread friction.
Wow, fascinating. All right, so how about if we did it with really slick lubricant? In that case, because there's not as much friction, I probably won't need as much torque to get to our target.
Correct.
So we used some of that industry standard stuff they call peanut butter, and we did a test with that. Let's take a look at what we got there for torque.
You can see that it's curved. We got up to the 880, approximately 76 foot-pounds.
So this is really interesting. So all three applications, we got the same amount of clamping force out of the fastener. The problem is I had a range of, on the low side, 76. In the middle group there we were at 86, and then all the way up to 119. So I think the answer is then it really depends on what kind of friction we have, or specifically what lubrication you decide to use.
The target torque we're trying to get to the clamp load will be highly dependent on the thread lubricant.
So there's not necessarily anything wrong with somebody choosing their own thread lubricant, except that you can't really give them any data on what to expect for a torque value to get that clamp load.
Correct.
On both ends of the scale, to make sure I understand correctly, then if a guy starts using, let's say, the peanut butter, he could actually yield the fastener by accident, not intending to, if he was using a torque value that was too high.
Correct. For instance, if we read our instructions for this particular product and it came and they wanted to know, well, what torque should we use, we would provide the answer from our lubricant, the torque point. If they ran on this particular run with the peanut butter, you'd see that you're getting upwards over 15,000 pounds of clamp load.
So roughly 1,200 more pounds of clamp force than we wanted.
That's still safe from going yielding. We established that the yield was taken on average of about 17,350. Now they're getting closer, but they're still under the yield in this particular case for this particular product.
So while they would be safe not yielding the fastener, is there any danger of them damaging or deforming the parts that they were trying to clamp together?
It would just depend on what those parts are. That's kind of out of our control.
Right. I guess the lesson that I want somebody watching this to get, though, is that just because you didn't fail the fastener doesn't mean that you're not moving your part out of the correct shape that it was machined to. And
correct.
You know, at the end of the day, the safest path for somebody to travel along is to buy your fastener and use the recommended lubrication at the recommended torque that you've done the science to find out.
We do a lot of effort, try to provide the best part and the best advice on torque, provide the lubricant, provide the nut, provide the washer, provide the fastener. We can control all those things. It's a fair amount of effort and time put into this so that they have the best product, perform the best they can.
Very cool. Well, thanks for taking some time to explain that to us. It gives us a lot more confidence in your product knowing that you've done all this research before we get it.
You're welcome.